Yeah. So welcome back. Session 2 today is by Shrikant Iyengar. Shri, session is
All
yours.
right. Okay, very good. So, we've been talking about this cellular approximations since the very beginning. So let me sort of recap what I said in the first two lectures. So let R be a ring, but at this point, you could take it to be either a DG, so differential graded ring, or even a ring spectrum. I never talked about any elements or anything like that. If you reflect on what I said before, really it was all fairly, I never dealt at the level of element, it was only at the level of object. So you can take R to be any one of these gadgets, and this will become important a little bit later on, and take M to be a R complex. And if you're in the DG world, you would want to take a DG R module, or maybe a module over the ring spectrum or something. Pick your poison. Okay, then, so as I had explained before, if you take any object in the derived category, now again, you then would construct the appropriate derived category. So in the world of DG rings, you can construct the derived category by again inverting the quasi-isomorphisms using a suitable model structure, and there's a similar construction for ring spectra. So you can cook up a derived category, and the main thing is that their quasi-isomorphisms become isomorphisms. So in that derived category, for each X, you can construct a natural triangle, exact triangle of this form. So there are, so the focus, I'll be focusing on this side of the triangle, because this side is sort of determined by this. And I sort of alluded to this, that the properties are such that the map, once you have this map with the properties listed below, this is unique. So you get a functorial third vertex. The crucial point is that this object here is built out of M in the sense that is in the localizing subcategory generated by M. Yeah. So remember, localizing subcategory meant that it's the smallest subcategory which is triangulated. So it has a 2 out of 3 property roughly, and it's closed under arbitrary coproducts, direct sums. So this part is built out of M, and it is the best approximation to X by things built out of M in the following sense, that this map is an M equivalence. By this, I mean that if you look at all collections of all maps from not just from M, but all the suspensions of M to X are to the cellular approximation, that's isomorphic to maps from M to X. So this map will induce such a map, and that ought to be an isomorphism. And notice the star here. One wants it not just from M, but also from suspensions of M, and for all suspensions of M, shifts of M. So you can express this in various ways. And one way you can say it is that it's an isomorphism. Now, forget the star. On whenever you plug in, look at maps from any object built out of M. So in this sense, this cell MX is the best approximation to X by things built out of M, right? And this is also equivalent to saying that there are no maps from M to, or even up to suspensions from M to the LMX, the third vertex. Before I move on, let me comment on two things, and this will become important later. You see conditions 1 and 2, they only depend on the localizing subcategory generated by M, not specifically M itself, okay? So really it's a property of the localizing subcategory generated by M. That's one remark. The other remark is, as I said before, do you think of this as sort of the best approximation to X by things in M? And this is what you would think of as a localization of X away from M, because M does not see this part of X at all. So you're sort of splitting X into two parts, one which is built out of M and one that M is invisible to M. Good. And what I want to do today is start off by explaining more or less a concrete model for this. I just said that this always exists because of some abstract Brown representability type results, but I want to give a concrete model. And this will come from thinking about Morita theory. So I already mentioned this before, the classical Morita theory. Let me state it in a slightly greater generality. So if you have two rings and an object M, which entertains both structures, both as an R module and an S module. So it's a bimodule. And I ask that both actions are on the left. Okay, then you can set up a pair of adjoint functors from R modules to, so for me, modules are left modules, so R modules to right are S modules. So as I said, these are adjoint functors, and this functor going from R modules to Ed modules is just this one, maps from M to blank, whereas the opposite way it's tensoring with M. So notice that on both times I'm using the left structures, and therefore here I need to stick in a right S module. So this is an adjoint pair that's nothing more than Horn-Tensor adjunction, and this induces an equivalence at the level of the additive category generated by M on one side and the additive category generated by S op on the other side. Op just means that I'm looking at right modules. And additive category means you're looking at finite direct sums of M and also allowing direct summands. So this is what I mean by the additive category. So on this side, so if you look at finite direct sums of S, you're picking up the finitely generated free modules. If you allow direct summands, you pick up projectives. So this is a standard quote unquote trick to convert sort of any additive category, additive category generated by any one object to sort of projectives. Yeah, this is sort of a projectivization process. You're making M projective over some other ring. Okay. And there are this context and its variants. Instead of taking HOMs, I could work with tensor products, or I could just look at HOMs on both sides. And there are various things you can do. Play simple games you can play to construct adjoint functors like this. So what I'm trying to say here is that this sort of construction shows up all over mathematics, and this is, basically the constructions that give you Koszul duality on one side. In algebraic geometry, this is how you sort of construct Fourier-Mukai transforms. And one can also see rational homotopy theory, the fundamental theorem linking this APL to simplicial sets as an instance of this phenomena. And there you would construct a simplicial object of DG algebras, commutative DG algebras, and look at maps into that object, either from simplicial sets or from DG algebras. So the basic setup is the same. Of course, in each context, you have to work more or less or impose some additional constraints to get something interesting, but this is sort of a very simple and fundamental construct. I also mentioned this so that I can bring up the word duality, and now I've just discharged my duties to talk about duality, and now I can do what I want. Okay, so back to where I was. So let now R be a ring and M and R complex, okay? So remember, I was trying to lead up to a concrete model for cellular approximation with respect to M, okay? So I want to look at the endomorphism DGA of M. So this is what I mean. And a concrete model for this is to look at HOMs from PM to PM, where PM is a cofibrant replacement. Of course, when I say cofibrant, I have a model structure in mind. I could take the model structure where the cofibrant objects are the semi-projectives that I mentioned before, right? So what happens now is that this is like looking at the endomorphisms of a module. First of all, I can view it as a DGA because, okay, so there is a differential already. A HOM complexes always have differentials. And the product is just a composition of maps. You're given a map from, I'm not looking at morphisms, I'm looking at all chain maps from PM to itself. So if you're given two maps, you can compose them. This is what endomorphisms objects, that's what you can do. And by the way, maybe I should make a comment. If, for example, if this is like a large matrix ring over R because it's a semi-projective. So let's just assume that the components of the projective resolution are all free. So here you have a large free module, large because M need not have a finite resolution. So these are two free modules, the same free module, forgetting the differentials, and you're looking at endomorphisms of the free module. There's nothing but a matrix ring. So it's a matrix ring with a differential. So that's what E is, the endomorphism DGA. And then M acquires a structure of a module over it, right? Because first of all, of course, M was an R complex, so that's already there. And what is the E structure? Well, it's just acting on the left, a composition. So this is how you can concretely realize the action. It's just saying that the endomorphism of a module acts on the module. A module is a module over its endomorphism. Sort of a almost trivial statement. So it's the composition. So now we find ourselves in the Morita context. We have an object, M. So in this case, I cooked up a ring S. So I have an object M, which has two actions, an R action and an E action. So you can set up the Morita context, except now it's happening at the level of derived categories. So you see, I've quietly slipped in the derived category of a DGA. But as I said, it's the same construct. You want to invert weak equivalences. You can do it by choosing a project model structure where the cofibrant objects are semi-projectives. And the way I defined semi-projectives, it was not specific to a ring. You just needed a filtration with good subquotients. Anyway, however you construct it, you get an adjoint pair, the Homs on this side and the tensor product on this side. The only catch is that you have to work with the derived tensor products on one, because those are the only functors that are defined on the derived category anyway. Okay, and the main point is that this theorem of Dwyer and Greenlees, which tells you that when M is small, so remember small meant that, so in the world of rings, this is just a bounded complex of finitely generated projectives. Or if you want to put it more categorically, these are compact objects in DR. So that's how you could think about it when R is something more exotic. So you have these adjoint functors, and what Dwyer-Greenlees observe is that these functors restrict to an equivalence between, on the one side, the localizing subcategory generated by M, and on the other side, the full derived category of the endomorphism DGA. The only thing, again, it's this op that comes up because of, this becomes a right module over E-op, over E, okay? Moreover, the co-unit map. So, when you have an adjoint pair, you have units and co-units. So the co-unit map looks so. So where X is now, I should maybe write this, where X is now in, well, it has to be, because it's a co-unit, X is in D of R. So X is in D of R. So you have a map like this. Again, this is just evaluation, right? If I've given a map from M to X, and then say an element of M, I can evaluate that map on that element to get something in X. That's more or less, this is what this is. The derived version of the classical evaluation map. So this map is the M cellular approximation, i.e. the object here is the cellular approximation of X with respect to M. So this, remember, M was small, so that will come up later. So this is the concrete model I was asking for cellular approximations. And it maybe doesn't look too concrete, but in fact it is, because you can write down everything fairly explicitly. So here's a sketch of a proof. So I had a colleague who used to say that every lecture had to have a proof and a joke, and they ought not to be the same. So this is my attempt at a proof. So as I said, so the first thing to check is that this pair of maps, these adjoint functors, actually restrict to the subcategory loc M on this side, the localizing subcategory generated by M. So for that, I have to check that if you apply this functor on the derived category of E or right E modules, you end up here. This functor lands in D-op is just nothing, saying nothing at all. That's the domain anyway of the functor. Range, okay. So what I have to check is that if you take a DGE module, a right DGE module, and that is in, not is, but if you take anything in DGA, you want to check that, oh yeah, correct. So I did write it correctly. So if you take anything, this is in the localizing subcategory generated by E, because after all, this is the localizing subcategory generated by E is the whole thing. This is just saying that objects have cofibrant replacements. So think of the case where E is just a ring, and I'm saying that every complex is built out of the ring, a ring, DGA. Every DG module is built out of the DG ring that it's defined over. So Y is in the localizing subcategory generated by E. And if you tensor with M, this is just by the exactness properties of the tensor product. Notice that it's derived. You end up in the localizing subcategory over R generated by E tensor over M with E. But this is just M. So that's triviality. So we do have that the functors restrict to functors between the localizing subcategory generated by M and the full derived category of the endomorphisms of M. And we have to check that this is an equivalence. And the natural thing to do is look at the unit and co-unit maps and check that these are isomorphisms in the derived categories. And these are the co-unit and unit map. So this is the co-unit, which is what we came up earlier. Let me call it epsilon subscript X. So X is now from the derived category of R, and this is the unit map from Y to this one. I'm just taking the compositions of the two functors in different orders. We have to check these are isomorphisms for all X in log M for this one, and Y in D of E for this one. Okay, and this again, the proof is standard. What you check is that you check it for the generator of the category. So we can check that EX is an isomorphism for X equal to M, because when you stick in M in the X component, this is just E. So the E's cancel, and this is just M. So it's certainly an isomorphism for X equal to M. Then you observe that if you look at the subcategory of all objects R complexes for which EX is an isomorphism, this is a localizing subcategory. Well, let me remind you, localizing just means that it's a triangulated subcategory that's closed under all coproducts. Okay, so this is an application more or less of the phi lemma in basic homological algebra, that if you have a diagram, a ladder with 5 terms and 4 terms are isomorphism, so is the 5th. So that tells you that it's a triangulated subcategory. And the main point is to check that it's closed under arbitrary sums. It's easy to see it's closed under finite sums. This saying that if two maps are isomorphisms, the direct sum is an isomorphism. But we want to check the same thing for arbitrary sums. And this is where we need to know that M is small. You see, if you look at this formula here, you want to replace X by if you think of an arbitrary sum of objects here, you want to move the sum outside, but that requires M to be small. So this is where the smallness comes in, and exactly in the categorical way, that it allows you to take a direct sum outside the Hom. Okay, so this subcategory of objects where EX is an isomorphism is localizing. It contains X, so it must contain localizing log M, because this was, after all, the smallest localizing subcategory generated by M. So this tells you that this is an isomorphism. This map is an isomorphism on log M. And a similar argument shows that this is an isomorphism on all of E, or D of E, because if Y equal to E, then this is just Hom from M to itself, which is just E. So that tells you E is in that category, and then you do the same argument. So this is a sketch of a proof. All right. So this is the proof of the theorem of Dwyer-Greenlees, that you get a concrete model for the cellular approximation when M is small. Okay. So at this point, I'll start writing again. Okay. So stare at this result here. Remember, I said that the cellular approximation really only depends on the localizing subcategory generated by M. So this leads to sort of a strengthening of the result of Dwyer and Greenlees. So, and this is based on the observation that, let me write what I said. Observe that this functor only depends on the subcategory generated, the localizing subcategory generated by M, not M itself. Okay, So this leads to the following. So here's a definition. Say, so we say M is, this is something that came up in the work with Dwyer, Greenlease, and myself. So this is, say, proxy small. If there exists a small object, W, with the following properties. So, okay, the first one is that W should be small. And the second condition now shouldn't come as a surprise, that they generate the same localizing subcategories. And I'm just saying that the localizing subcategory of M has a small generator. So these two are sort of reasonable things, but actually it turns out there's a third technical condition that's required. It sounds technical, but it's actually rather crucial, that W is finitely built out of M, meaning i.e. can be finitely built out of M. Okay, so although M itself may not be small, you can construct a small object in finitely many steps that generates which is a generator for the localizing subcategory. And then the Dwyer-Greenlease theorem extends to this. Then again, and then again. So it's clear that you could write down the model for cell using the endomorphisms of W, but the point is you can use the endomorphisms of M again. And this is so I'm careful to write only the statement about cell. So this is of M. By this I mean, of course, the R HOM. I should really maybe put an R here. Okay. So just keep this in the back of your mind, that this cellular approximation, the good model for this model for the cellular approximation works also as long as you have proxy small objects. So this turns out to be rather powerful. So this is to be useful. And this is useful only if I tell you that there are interesting contexts where you can cook up proxy small objects. But I'll get to that later in the lecture. So now let me change tack and try and convince my commutative algebra friends that they know all this already, or they've seen this in a different guise. So this is back to local algebra. This is the second part. Commutative Noetherian rings. And now this begins to link up with what Suresh has been talking about. So R will be one such, R a commutative ring. All right. And let me fix an ideal in R. And so it's not the whole thing. And let me take V to be the closed subset of the Zariski spectrum of R. So the closed subset, corresponding closed subset. Yeah, the Zariski topology. This is with the Zariski topology. In fact, these are the closed subsets that define the Zariski topology. All right. Now, for any X in, or maybe I want to deal with modules. Okay, why not? Let's start with X in mod R. I want to look at the sections of X supported on I or V. So the simplest way to do it, to relate to what Suresh said, is to take this to be the global sections of V on the sheaf on a spec R defined by X. Okay, so these are the sections of X tilde supported on V. So what is this? So this is just looking at, now these are the global sections of X supported on V. So the global section of X tilde are just things in X. So these are X and X tilde, X and X, such that you want them to be supported on V. So X localized at X is 0. So X is 0 in all local rings, not on V, not in V. So i.e., so this is, there's a natural map from R to the localization. So you're looking at the local ring at the point P, if you wish, and you want to say that this goes to 0 here. So this is the same as, this is basically the kernel of the map from X to product of P not in V, i.e. P does not contain I. That's really, and just painfully unraveling the definitions. Now this has also another way to look at it. These are looking at elements of X such that I to the nx is 0 for some n. So this is why this is sometimes called the I power torsion submodule of M of X. So this is the of X. All right. And now I want to look at the derived functor. So Suresh already talked about for all X in X. Instead, I could take a module, or I could just go set R gamma RV and write Ri to the right derived functor of this. So this is sheaf cohomology really, or cohomology, and then it efforts left exact, and you're taking the right derived functor, evaluated on X. And how would you compute it? Well, you could replace I by an injective resolution, which is what Suresh did, right? He took an injective resolution and apply the gamma functor term-wise. I is an injective. And I have to say injective in quotes, it depends on, when you're not looking at modules, you have to, just like, the distinction between projective resolution, since you want to be careful when things are not bounded. It's the same thing here. But that's just a technicality, so let's not get hung up on that. So you just replace X by an injective resolution and take its derived functor. So this goes by the name of the local cohomology functor in local algebra, and the cohomology of these objects is precisely the local cohomology of I supported on X. Is the local cohomology of X supported on I, other way around. On I or V of I. Okay, so this, this inclusion here, so it gives you a natural map. It comes with a map. So there is a natural map. From X to X. After all, you're looking at the P, this is only picking up the piece of X or injective resolution of X supported on I. So there is a natural inclusion at the level of injective resolutions. And I wrote it this way to make the claim, and this is a theorem or a fact, okay, that this is the cellular approximation. So this is the R mod I cellular approximation of X. So I is an ideal. This is the of X, i.e. is, really I should be saying that this map is a cellular approximation, but okay, it's just so how do you prove this? Well, it's actually, well, I don't think it's that difficult to prove. So it's more or less clear. Well, you have to show that this is in the localizing subcategory generated by R mod I, and that this is an R mod I equivalence. Okay, and it's not terribly difficult to do this, but let me skip the proof. It's sort of clear that this is built out of R mod I because you're looking at the piece supported on R mod I, and showing that this is an R mod I equivalence is also not such a complicated thing. Okay, now this equality ought to make both algebraists and topologists happy. The algebraists because it says the cellular approximations are nothing but local cohomology, at least in some contexts, and they should make the topologists happy because he should tell them that local cohomology, which is somewhat mysterious, is nothing but cellular approximation. And in fact, this is how it gets used in, it also means that, any intuition you have about local cohomology transfers to this side. You can try to see what it's saying about cellular approximation and vice versa. Both communities have developed different insights on these objects, and this allows you to compare those insights and exploit them. This will come up later on. So what I want to do, yes. So what I want to do next is the following. So, well, this does give you a model for the cellular approximation in terms of R mod I. This is in some sense unsatisfactory because I've been staying very close to rings or DG rings here by talking about injective modules and this and that. And actually the injectives tend to be rather complicated. So one would want a good model for this. So what are the better need good models? So would like good models for cell R mod IX. And this is something the theme I've harped on before. So you want to find good models for this. And one thing you can say, so this is where eventually, so I should remark here that, so there's a note that R mod I, it need not be, is typically not small or not even proxy small. I'll comment on this point in a bit. Okay, so for now, just take it as if you know this already, that's fine. But otherwise, just take it as a fact. All right. So what you can do is the following. So this allows me to bring up Koszul complexes. Okay. So what's a Koszul complex? So here's a quick, so given an element in R, the Koszul complex on R, which is K of R, so is by definition the following. So any element in R gives you a multiplication, just take an element of R and multiply it by R. So think of R as complexes in degree 0 and look at the mapping code. Okay, so this sounds a bit silly, but all you get is this complex. This is in degree 1. And this is a degree 0. So this is the Koszul complex on one element. And you can construct the Koszul complex so on any sequence, a sequence in R. You can construct the causal complex by an iterated mapping cone construction, or you can just take the tensor product. All right, just the usual tensor product. And this is where I'm dealing with commutative things. So at this point, if you're dealing with DG rings or spectra, you want to be in the commutative context, or anything that allows you to take tensor products. You don't need it to be strictly commutative. Okay, so this is the causal complex, and why is it relevant? Okay, to what we are saying. So given I, choose a sequence R such that it's a sequence of generators for the ideal I. Then what you can do is you can look at the causal complex on R. So K equal to K of R is such that it's just, first of all, it's small, i.e. a perfect complex, which you can see immediately. You know, it's for one element, it's clearly perfect. It's just, in fact, it's what is one definition of small is that it's in thick of R. Here I've explicitly building out of R by taking a mapping cone. And if you take a tensor product of these, you'll see that you have tensor products of complexes like this. So that's a finite free complex. So it's clearly small. So the second thing, and this is also not very hard to prove, is that the localizing subcategory generated by K is the localizing subcategory generated by R mod I. This is also not very hard to prove. Okay, I'm not putting the third condition down. I'm just saying that about proxy smallness. I'm not saying R mod I is proxy small, only that the first two conditions satisfied. Thus, the cellular approximation with respect to this is the same as a cellular approximation with respect to K. But now this is small, so I can use the good model for K. So namely, E, K, where E is now end RK. Or I don't even have to take the derived endomorphisms because K is already cofibrant. It's a finite free complex. And again, let me emphasize, this is just now it's even a finite matrix ring with a differential. So if you forget the grading, it's just a matrix ring over R. It's a finite with a differential, of course. So it's something fairly concrete and simple. So the way I look at it is that this gives you a sort of an interesting model for local cohomology, computing local cohomology. So thus, I do have to take derived though, because K need not be cofibrant as an E module. It's this. Okay, and this turns out to be rather useful, and I'll come to this later in the next lecture. Now, this is for a general I. Now, as I've already said, any comments so far, by the way, before I move on to the next step? Any questions? So this is the best you can do in general. Now, under some special cases, you can do better. And this is well and good for explicit computations. But again, the trouble is that this K is not sort of functorial in I, because it depends on a choice of generators for I. So that's the issue here. But one can do better. So here's an exercise to get some feel for this. So suppose you take a prime P, it's a P in spec R, is such that R mod P is a regular ring. The ring is regular. Is regular as a ring. Yeah, i.e. the global dimension of R mod P. Regular in the usual commutative algebra sense, which just means that any module has finite projected dimension. Any finitely generated module has finite projected dimension, say. So in this case, you can show that then R mod P is actually proxy small. It need not be small over R. In D of R. Oh, by the way, there is the result of Hopkins that I mentioned last time tells you that in fact, Kp, so K of R, where you choose any generating set for R, is a small proxy for R mod P. I didn't introduce this language, but this just means that this is plays the role of W. So this is E. So we already know that it has the 2 out of 3 properties. All you need to know is that R mod P finitely builds. So KR is in thick of R mod P in DR. Okay, so take this as an exercise. Try to show that the causal complex on any generating set for P can be built out of R mod P in D of R. You have to use the fact that R mod P is regular. So this applies in particular for closed points. So whenever you take M to be in a closed point in the Zariski, so a maximal ideal in R. Because then R mod M is just a field. So what you get is that R mod M, let me call it K, the residue field at M is proxy small. And the causal complex is a witness. Okay, so you end up with the formula for local cohomology, which will be useful later on. So if you look at the local cohomology supported on this closed point, so it's which I should have written R mod or M here. I'm writing V of M. Okay, so this is given by R hom K, and this is R end of RK and K. So for example, if you're looking at special cases when you're looking at local algebra, is a local ring. So this is the maximal ideal of the ring. And this is the residue field. Okay, so for example, if you look at the vertex of the affine variety associated with the projective variety, then this this formula applies. So this will tell you that if you want to sort of this gives you then a model to compute chief cohomology for projective varieties. So you can write this here computes local cohomology. So this just may not look too appetizing because it involves this thing here, this endomorphism DGA, but what is the cohomology of this? For the rest of the talk, it's all remarks about this thing. So what is the cohomology of, okay, what are we doing when we're talking about the cohomology of this? So if you look at RK, these are just the X groups. So this is, which is, this is typically highly non-commutative ring in general. So this is a graded ring, typically highly non-commutative. So this is a ring with the Unida composition. So this is relating local cohomology at the close point to something about the this X algebra. And this should, at least the commutative algebras here, should see the connection to causal duality. Because causal duality okay, can you still hear me?
Yeah.
Anand? Good. I somehow lost the connection for a second. So this is sort of relating local cohomology to properties of this causal dual algebra. I mean, this makes sense when R is, you can talk about this in the graded world, then, and if R is a causal algebra in the commutative algebra sense, then this is, this begins to look interesting. It also tells you that, so in particular, the special case of interest is when you look at the ring itself, and then you're looking at this gadget here. And this begins to tell you that the X, so this puts a focus on these guys. So what's the cohomology of this? Its cohomology is, its cohomology is X. RKR, right? So this again anticipates the role of Gorenstein rings in this whole story, because I'll make a definition here, but I won't say much more about it. I'll pick up this theme in the next lecture. Gorenstein means that, so this is a definition. R is, okay, so R is Gorenstein. If this X group is as simple as it can be, so it's just a copy of K, but in some degree. So this is just saying it's in degree A. A has an important role. It's called the A, it's the A invariant or something. No, this is not the invariant. This is just in some degree, and it turns out to be the dimension of the ring. So let me put it as D. So it's a copy of K in some degree. So you can see why this condition, the Gorenstein condition, is, the Gorenstein rings are special in the context of local cohomology, because it's saying something about this object here that goes into computing local cohomology of R. I'll discuss this next time. So today I just want to make some more comments about this formula here. So this is saying that, this, at least for local rings or close point in the spectra, you can, there's a different model for local cohomology, at least that's new in the commutative algebra context. The next thing I want to return to in the last few minutes of my talk is the business I talked about, proxy smallness. So returning to proxy smallness. So we want to know, so if we were looking at R as a ring and commutative Noetherian in our case, and it is interesting from this perspective of cellular approximations to know, so we wanted to know where when these, interesting to know when R mod I is proxy small for all ideals. Okay. So this brings me to the following result. So here's a theorem. So R is locally computed. So R is, let's say R is a local ring. Actually, I don't even need to state it for a local ring. So R is a commutative Noetherian ring, is what is called locally complete intersection. If and only if each X in the bounded derived category of R is proxy small. It builds a small object which generates log X. All right, so this is actually, this combines the work of a lot of people. There's the work of this, in the first instance, when R is I haven't told you what a locally complete intersection is, but the commutative algebras know it. Just locally is just saying that at every localization, it's a complete intersection. And I won't get into the definition, it's not particularly important, but I can just tell you that this is an important class of rings that comes up in local algebra. So one direction that when R is complete intersection, that everything in DB mod R is proxy small was proved in this paper that I mentioned earlier by Dwyer, Greenlease, and myself. Then the converse is a very recent paper, less than 2 years ago, by Josh Politz, and actually also using results of Yadina Letzt. And this should be compared with the following classical result, that this is due to Auslander, Buxbaum, and Sayre, that R is regular if and only if each DB mod R is small. That means it has, it has a for example, every finitely generated module has a finite projective resolution. So this is an old characterization of regularity, in fact, from the 1950s and 60s. So this is due to Auslander, Buxbaum, and Sayre. Okay, this is a famous homological characterization of regularity, which has all sorts of interesting consequences. So one can, the thing about this, you can think of this in terms of homotopy theoretic terms, that the regularity of a ring is detected by the derived category of the ring, the bounded derived category, where that every object is small. And this is a similar characterization for the locally complete intersection property. It's something involving only the triangulated category structure of the bounded derived category. That it's saying that every object builds a small object which has the same localizing subcategory. So these are categorical or sort of homotopy theoretic characterizations of regularity and the locally complete intersection property, which makes it possible to think about these concepts in topology, for instance. And in fact, what I'll do in the next lecture is discuss how you can think of also the Gorenstein condition in topological terms, but actually the story is already here. I've already told you what Gorenstein means in terms of these objects, but all these things you can make sense in topology. But I'll get to this in the next time. In the last let me take a couple more minutes to say something else. I had originally intended to discuss also completions. Let me quickly say where that comes in. So back to the general context, and maybe so back to R ring and M and R complex. So the Morita context was looking at functors or the derived Morita context. So you set up functors from two derived endomorphisms of ring. So this is what I called E, right? So let's call this E. So, I said that there was the tensor product over E, M, and that was left adjoint to the Hom. So this was Hom M blank. There's also another functor. So when M is, so now when M is, so let me write it like this. So M is, let me say that M is small. In this case, there's also a functor. This itself has a right adjoint. M hash blank, where M hash, so M is a left E module, and one then gets a right E module by dualizing with respect to R. So this is now a right DGE module. Okay, so you can construct this functor here, and it turns out, and this is where you need to, you can always write down this functor, I think, but it turns out when M is small, this is right adjoint to this. So in fact, you have the beginnings of what is called in the world of triangulated categories anyway, a recolma. this functor has both a left adjoint and a right adjoint. So then it's interesting to play off and see what happens if you compose this functor. You play out and see what you get from this functor. Then, again, this is Dwyer-Greenlee's theory. If you take any x in dr, so you get a map now, because the role of left and right adjoints have changed. This has become the left adjoint to this. What you get is a map from, let me see if I can do this. So this is, so there is a natural map like this. Again, it's coming because it's an adjoint functor. So this map is derived completions in the context of commutative rings. In local algebra. So if you specialize to commutative Noetherian rings, then this gives you a derived completions. And what Dwyer-Greenlee's prove is that you have this thing from local cohomology. So let me call it, so we have D of R, and we have D of E op, and then we have D of R again. So it's the other way around. It's this one, the EFC M. So we saw that this is, we have these functors, and maybe I won't write this down. So it's still this, we have this. M hash blank. So this restricts to an equivalence, as we discussed before, between the torsion, so lock M, so the M cellular objects, and the E op, and on this side, it becomes equivalent to the M complete objects. So at the end of the day, you get a equivalence between the M torsion or M cellular and M complete objects in the derived category of a ring. So this explains the title of the paper, complete objects and torsion objects. So somehow the completions and torsion and cellular approximations are in some sense different sides of the same picture. I won't say much more about completions, but in my next lecture, I'll go back to the cellular approximations and this model for local cohomology and talk about how this leads to some duality. Okay, I should stop here. Thank you.
Thanks, Srikanth.